Welcome to Study Loop.
Okay, so we have 0.25 moles of gas at a certain pressure at this temperature, and its state changes in the way described in the problem, and kind of ask a few questions about some missing quantities. So first, it first expands isobarically, compressed thermally, isothermally back to its original volume, and finally cooled isochorically to its original pressure. And so first, let's draw a PV diagram, and I went ahead and wrote down any of the numbers that we'd have to use. And so I might put subscripts on them later. For now, I'll just leave them like they are. Okay, so here's A. Let's get our PV diagram going. Whoops, P, V. And so it first expands to twice its volume. And maybe I'll label those in a bit, but we can just remember that it gets twice as big. And then isothermally, it increases its pressure. How much was it? Come back to its original volume, right? And then finally, it stays at the same volume isochorically. And yeah, it goes back to its original starting point. So I'm going to label these 1, 2, and 3. And then now I'll put the subscripts on. So this is its original pressure and temperature. And then the N doesn't need a subscript because it stays the same. All right, now to get more quantitative. So B, it asks for the temperature during the isothermal compression. So we need to kind of know what's going on between 2 and 3. So let's see. So first what I did was I said, let's find the volume. Maybe there's a different way to do this. I started to think of one as I started to write this. But anyway, I'm going to do it the way that I originally wrote, which is to figure out the volume. So at point 2. So I know V at 2 is just 2 times the volume at 1. But we don't know that. But we can always invoke our favorite equation. PV is nRT. So I'll just kind of put it up here. Whoops. PV equals nRT. And if you rearrange that for volume, then you can go ahead and sub that in here. So that's 2 times nRT over P. And if we write it that way, it looks like we have everything that we want. So yeah, and then of course we can use we have our R value. I guess I can put it over here. So R, the gas constant, what is its value? Whoops. 8.315. 8.315. And forgot the units on that. Let's see, is it, it's joules per mole Kelvin. I'm just thinking in my head if that actually makes sense. So it needs to come out into units of joules. So yes, times moles, yes, times Kelvin. Okay. And I have units on everything now. Okay, great. Back to the problem. So yeah, if you just take the numbers that I have in this box and plug them into this equation, you can get the volume at 2. So then if, so when I calculated that, let's see, what did I get? So I got 0.00615, 0.00615 meter cubed. And then great, now I can figure out the temperature. So then I can say T at 2, which is equal to T at 3, by the way, is equal to P at 2, V at 2 over NR. Something keeps messing up with the, there we go, with the N. And then, yeah, we have all of those, P at 2, which is equal to P at 1. And then, so if you take in everything, all the variables, and plug that in here, then maybe you will get what I got, which is, let me check my math, 710 Kelvin. So does it make sense that it got hotter as you expanded the volume to keep the pressure the same? Yes, it does. I like to think of pressure as kind of how the impact of the molecules hitting the surface of the container. And if you're going to expand the volume, I think naturally there wouldn't be as many collisions with the container. So if you want them to have the sort of same impact on the container, you have to sort of tune up each molecule's speed, or each atom's speed. So that's just how I like to think of it qualitatively. All right, I'm going to go ahead and box this up so it doesn't look super messy. Great. And for part C, it asks for the pressure. Right, let's double check the maximum pressure. Okay, the maximum pressure is pressure at 3, so we need to find pressure at 3. So if for isothermal expansions, you can say that the quantity PV stays the same, and that's just because for isothermal, nRT stays the same, assuming the number of moles doesn't change, and of course R is a constant. And by construction, T doesn't change if it's isothermal. So you can say P2V2 equals P3V3. And from that, you get that V2 equals 2V3. Or not from that, but we know that V2 equals 2V3, because that's what the problem said. And then therefore, if you plug that into here, then you get that P2 equals 2P1 equals 4.8 times 10 to the 5. You don't even need a calculator for that. Woohoo! All right, an area under the curve, I will go ahead and add another, sorry, to not area under the curve, that's jumping ahead. First, D, they want the work done by the piston on the gas during the series of processes. So it's unfortunate I have to go to another thing because I kind of want the quantities, but whatever. So the work done by the gas, is that what they ask? Actually, let me double check. Done by the piston, right, is so it's going to be the work done along 1 to 2, so the isobaric expansion, and the work done from 2 to 3, which is the isothermal expansion, and then there's no work done from 3 to 2 because the volume doesn't change. And so for 1 to 2, the work is P times V2 minus V1. Yeah. And then for isothermal expansion, then, or volume changes, I guess more generally, it's nRT ln of V3 over V2, like, or in general, the final over the initial, which is the area under the curve of a 1 over X, if that's meaningful to you. And so, yeah, I think if you plug in everything here, acknowledging that, of course, V1 equals V3, and then V2 equals 2V1. If you plug that in, and then let me put a subscript on the pressure. And and I need a subscript on the temperature as well. So I'll call that V2, or T2. So I think, yeah, if you plug in the numbers, they're going to be opposite signed. And the log will come out negative, I believe. Yes, the log will come out negative. Yeah, and then you should get minus 285 joules. All right.